Good morning, good afternoon, and good evening, everyone. My name is Francesca Novara, and I'm happy to welcome you to Data Day, a virtual event in which we're going to talk about the use of data in chemistry and chemistry research from multiple perspectives. This event is brought to you by Chemistry Europe, your society publisher, and an association of 16 European chemical societies. Before leaving you with the expert, just some housekeeping remarks. We highly welcome any questions for the speakers and the moderator. For these, please use the questions function in the square that you see on your screen. And should you have any technical difficulties, please reach out using the chat function. We are also very lucky today to have Anne Nice with us, and she will help you with these questions. I'm very happy to let you know that this event will be recorded, and a recording will be circulated in the next days. So feel free to go back and watch it again in case you've missed something. And now I would like to introduce our chair for this event, who will also introduce our two speakers later. Pedro Mendes. Pedro studied chemical engineering at the Instituto Superior Técnico in Lisbon, Portugal, where he also received a PhD in 2017. Then he spent some time in Belgium for a postdoc, and he returned then to Portugal, where since 2021 is assistant professor at the Instituto Superior Técnico in Lisbon in the field of heterogeneous catalysis and multi-scale modeling. Pedro has been actively promoting open data practices in the field of catalysis and training young scientists on fair data sharing. Recently, he has also been appointed Open Science Ambassador for Catalysis by the Research Data Alliance and the European Open Science Cloud. Pedro, we are very lucky to have you with us today. Welcome to Data Day. The screen is all yours.
Hi, everyone. Thank you, Francesca, for this very nice introduction. It's a great pleasure to be here today. And my role here is to spike up the discussion, and I would like just to start with a quick introduction on open data and why open data is so important today. I hope you can all see my screen at this point.
Yeah. Okay. Yes, yeah, Pedro, we can see your screen, and you can go ahead. Okay. Thanks.
Okay, so why open data? Let's start some 250 years ago. In fact, curating data has been very important in the scientific process. In the case of the periodic table, during many years, in fact centuries, researchers had to curate data, keeping all the experiments and the research they did about the elements, such that at the end, Mendes could take all the pieces of the puzzle together to make up the periodic table. For instance, there's Sir Humphrey Davy. He discovered, among others, sodium and potassium in the early 18th century, and the periodic table only came up 60 years afterwards. It was obviously already dead at that point, and it could not be acknowledged by his contribution to the periodic table, but he was acknowledged in life by his great capabilities on fully reporting the experiments he made and bookkeeping all the data he found. He also published a book in which he notes about failed experiments and so on. So this is the key job he left us. What about today? So today, as you can see in this graph, we have a bit of a different situation. So on the axis, you can see the ratio between published data sets and articles published on a given field. So of course, it's a very simple metrics. Won't tell you all the reality, but I think it's still quite interesting. What you can see is the average on all disciplines in purple, and this is about 50. So that's 5% of data sets as corresponding to articles published. We see that some fields, especially biology, is quite advanced on this, so they have very good practices on sharing data. This is this is potentially fostered by the Human Genome Project that you will all know, in which there was data sharing at an incredible scale. But chemistry is not doing so well. In fact, we are a bit above the average. And if we take the applied fields of chemistry, and so particularly chemical engineering, we are really basically not sharing data. So this is very different from the picture I just gave you on what led, on the trail that led us to the periodic table. I mean, there can be many reasons for this. There's the so-called crisis of science. First, there have been reports for decades now, or for a decade now, on research that cannot be reproduced, results that are not repeatable in different labs, which is a great problem as we are building up on each other's work. This, of course, has a cause, publish or perish, so the pressure to publish is one of them, but not the only one. But the point I want to make here is that we need to work on this to make sure that our data is reproducible again, such that we can trust each other's data and build on that to come to greater conclusions. So with this, I hope I said what is open science about, and I think, in fact, a very good example from recent years is the COVID pandemics. There we were obliged to share data again in a precedented scale, and open science is all about breaking barriers to knowledge, and is to improve science collaboration, and this is something we have seen through the whole COVID crisis. What I also want to give you as a first perspective, and hopefully to open also the debate that we'll have afterwards and the Q&As, is that open science can be fostered and you can promote open science in many ways. So since the first stage of research, which is here represented in gray, so we start with a biblial search, then you do analysis of your data, there's the writing, there's the publication. Through all these stages, and whenever you're comfortable on your project and best suits the project needs or confidentiality requirements, you can share data in many ways. So these are, of course, a great list of examples, but you can even share presentations as we are here doing today. So my presentation will be openly shared, and you can, that's a way of contributing to open science and breaking barriers to knowledge. I will skip this because Sonja will dwell on this, but I think a big issue we are also trying to disentangle today is that people think open science is too difficult and requires too much effort. I don't think that's the case. If you don't know where to start, you can start on the FAIR principles and finding out if there are standards for your own field, and that you can do at fairsharing.org. Herres Future, for which I'm an ambassador, also wants to help us here. So Herres wants to help make the European research first more innovative, more streamlined, and easier to reproduce. So on the way to open science. Herres Future is providing services on many steps of the data cycle. So from data discovery to computing services and integratable services, we have already much data and many models that came out of that data. So there's much we can do. Herres is putting some pieces on the puzzle, and I think from Sonja and Teodoro we'll also listen to great examples of what we all can do and how can you also give your first step in open science and open data after today. Just like to finish up with some quick acknowledgements to everyone that has been working with me on this. And after this first introduction, I don't think we need a Q&A. It's really only to get your ideas to boil in some way. I will introduce Sonja. So Sonja is a professor for bioinorganic chemistry at the University of Aachen in Germany. She studied chemistry at the University of Paderborn in Germany as well, where she also received her PhD. After a postdoc at Stanford University, she worked at several universities in Germany before becoming a professor in Aachen, where Sonja holds a share of bioinorganic chemistry in Aachen since 2015. In addition to her interests in this field, she's heavily involved in the transition towards open science as part of the NFDI for Chem team. By the way, I'm super curious on what you'll present today on this great initiative. I think it's unique at the European level. And since 2020, she has been a co-speaker also for the NFDI for Chem, being responsible for the task area of community and training. So we are so happy to have you today, Sonja. And she has also been awarded with many prizes, namely the Momentum project of the Volkswagen Stiftung for Sustainable Machine Learning Applications in Chemistry. And she also became a Chemistry Europe Fellow this year. So thank you for being here, Sonja, today. I really look forward to your talk and to learn from you on how we can share our data and what great things we can do with it.
Thank you so much, Pedro, for the wonderful introduction. I would like to thank the Wiley team for inviting me to this Chemistry Europe Data Day. It's really a great audience, and to have here all the people interested in open data and fair data. And I tried to share my slides. I'm not sure if this is working at the moment. In the test run, it worked.
So we can see your emails now.
Ah, you can see my emails. That's funny.
Yes.
Yeah, okay.
There we go.
Then you see a lot of NFDI for Chem emails. Do you see now my PowerPoint slides?
Yes. Yeah.
Aha. Okay. This GoToWebinar is a little bit different than Zoom or Teams. Okay. So NFDI for Chem. Now you see my slides.
Yes. Yeah.
Aha. Now we are set. Great. Okay, yeah, dear ladies and gentlemen, thank you so much for being with us in this webinar. I would like to talk today on open data in chemistry because it's a continuous and cultural change. So I would think that 2 years ago I had given different talks on this because technically not everything was possible, which I can show you today. And I think in 2 years or 5 years from here, there will be even more interesting solutions. But it's, I think it's a challenge, and society and also science has to undergo the challenge towards open data and fair data in the next 5 or 10 years. And there are a lot of hurdles, and how we can tackle these hurdles I would like to talk about. But perhaps for all the people who know me, they know I'm a traditional chemist. I'm coming from bioorganic chemistry, from coordination chemistry. So I would say 80% of my group are doing real synthesis in a real lab, real spectroscopy, also mixed with theory. And some part of my group is now turning towards electronic lab notebook development and software development. But all the questions we are dealing with are really coming from classical chemistry, synthetic chemistry. Okay, perhaps some words about the evolution. Oh, now I don't see my slides again. That's strange. If I don't see my slides.
So we still can.
You can, but I can't. That is a problem. I have the impression that this GoToWebinar is really a funny thing. Here are my slides back. Okay. Now the slides. Great. Yeah, thank you. So if we look at the speed of evolution between 20 to 30 years, we came from room filling computers. So the first Cray computers really filled a full room, and now the computing power of just a mobile phone or any iPhone or even cheaper phones can substitute the old computers. But if you look at chemistry, if you just compare lab notebooks on paper from the 20s or earlier and from today, then we are still stuck in some similar way of noting experiments, how they are done, what we observe. Although we have super cool machines in the laboratory, we made a survey that 20% of the chemists are using electronic lab notebooks, and the rest is still hesitative and stays with paper lab notebooks. And that is really funny because via NFDI we have contact to a lot of other disciplines, and I think everyone working in humanities has in today's world the problem or the possibilities and the tools to work digitally with texts of Goethe or Schiller or with church windows. So every branch of cultural humanities in science, they are already digitized, and we as chemists are still noting and drawing our wonderful molecules and noting the results, what happens there. So this is quite traditional. And if we go a little bit further, then we have the problem that we are working on this paper notebook, that we are storing the data still on terabyte disks. So I have a lot of colleagues all over Germany, not especially now in Aachen, who don't have an admin in their laboratory and have still a working group server somewhere in the corner, which moves from every computer to another one. So really old-fashioned to store all the data. But on the other side, we have wonderful NMR setups or X-ray machines or Raman spectroscopic setups, and they produce more and more data in a higher resolution. They produce faster data from day to day, and these data are digital. But in the end, the students are really often sitting there making the analysis, for example, of the NMR data in a digital mode. But then they type in the final results, the final assignments, they type in manually into a Word document for their thesis or for their publication. So this is really not a good way, because many typos can get in, and I know a lot of laboratories which are still working like this. And what is happening with the data in the end? So you write a publication with some text and some nice figures, and then you have the supporting information. And in the supporting information, you show the PDF show the figures of the NMRs. Sometimes there are still manual assignments of the mass spectra, for example, or you show chromatographic data. But in the end, all this is buried in the PDF document, and there it's not machine readable. So coming to Pedro's introduction, this whole workflow is unfair in the meaning that the data are not findable, they are not interoperable, they are not accessible. The A is for accessible, and even more, they are not reusable. So in today's digital world, this would be better to have a full seamless workflow, a digital workflow. This is a little bit, this is in German, but the DFG has published this in German. So we have now from our funders, the German Research Foundation is the main funder in Germany, and they have published the guidelines for the good manufacturing, for the good scientific practice, that it's important to store data, and they try to force the scientists in Germany to think about fair data, open data, to put the data in repositories. And I mean, there are also practical questions coming up in research. So my group is now running for a little bit more than 15 years, and I see that there are questions arising. Where are the NMR data from 10 years ago, and where are synthetic details? So normally I was the memory of my group, and if the student asked me who did this crystal structure, who did this, where is the structure code of this cobalt or copper complex, I knew this out of memory, because we didn't have so many structures. I would say 100, 200 in the first years, and I have a good memory for this. But now the group is too large, and perhaps the memory is not so good anymore. The producibility, the production mode of the group is so high that there is so much compounds coming up that we need some kind of better archive in the group. And so good data management makes a group productive, more productive than just having it all in paper notebooks and scrabbling through all these notebooks in the end. But there are, of course, colleagues who say, that is critical. It costs time to my students. It might cost money. There are a lot of lab notebooks out there which are really expensive. I don't name any names here. I will dwell more on those ones who are open source. And it's always a question, do I really need to do this? I mean, in EU projects, as Pedro said, it's mandatory. In DFG projects, it also becomes mandatory. But in a lot of projects, it's just about the question if it will become mandatory or not. And there are also quite critical colleague statements who say that the supporting information is totally sufficient. I mean, all the figures are in supporting information, but they are not machine readable. And also some colleagues just say straight out, no one else does this. Why should I care? Yeah. And it's also a better time invest when the students are being at the bench doing all the experiments and not sitting too much time at the computer. So a lot of colleagues really told me this. And our vision now in NFDI for Chem, and I have the honor and pleasure to speak a little bit for the whole consortium, is to provide all tools as user-friendly tools to the chemists for the full data life science. So we have to get away from the linear way of seeing data. There is someone who's producing data, then they are published, and then they are stored somewhere, but that we are producing so much data which in fact is paid by the taxpayer, say it's DFG money or EU money or other funders' money, more namely it's taxpayers' money, that is important knowledge for the upcoming generations. And so in the better cycle, it would be that we have, for example, our experiments, the data collection, the data processing, the data analysis, for example, the NMR data, that can all be done digitally. Then the data are preserved, they are published, but in a digital, fair way. And then they can be reused, for example, for a meta study on drugs and their NMR spectra, or for example, for methods of machine learning. I think Theo is here as a really cool specialist, and they are happy to have data which are well curated, well annotated with all details, and not just a photo of a paper notebook somewhere. And then the cycle starts again, because out of these data you can go into more research. But herefore we have to help chemistry to get into a digitized world, to evolve standards. So how to report an NMR spectrum in a standardized way. There are already standards, but no normal chemist does know it. But there are also a lot of methods where the standards have to be developed. So for example, EPR spectroscopy or Raman spectroscopy, they are really working groups to think how to publish a Raman spectrum in a fair way with all the metadata to really help that these data are also readable in the next 10 or 20 years. I mean, the problem is also, a lot of you have encountered this, that if you have older data, old means I would say 10 years, sometimes old files cannot be reopened because the license is gone, or the files have some strange damage, or you have Word documents with funny red crosses in boxes because it's 10 years old for some results. So here need to be really standards which are surviving 10, 20, or even longer, I would say 50 or even 100 years for the next generations. And we have to talk to the community about the needs, and we have to teach to the community. So going a little bit further, teaching was now the key word here. I'm also active in the NFDI section, education and training, together with Peter Pelz. We're leading it, and we need really good teaching materials to teach all career levels. So we have to convince the professors that open data and fair data is important for the development of science. We have to help the researchers to get to the right tools, help the students, but also teach the next generation already. And here we are developing materials for the faculty, but also for the research. For example, we are providing RDM workshops in NFDI for Chem. We have Chemotion Q&A sessions. Chemotion is our ELN and repo open source tool, which is quite practical. We have videos, and we also integrate this in Aachen into lab stages to train the coming generations. Going a little bit further, I would like to show some of these examples. So just from this year, I would like to point to an article where we were working on a lot of copper complexes for electron transfer. So this is some branch of bioorganic chemistry. So we produced a lot of guanidine ligands, and from there we went to the copper complexes, and we did a lot of spectroscopy, crystal structures, DFT, and yeah, then a lot of this stuff has to be deposited, because normally in the paper we only would publish the figures of the NMR data supporting information. We did it because it's standard in that chemistry, but moreover we also published then the links to the Chemotion repo, and that is quite seamless, which means when the students are using the Chemotion ELN in research, the electromagnetic network book, just by hitting a button, the data can be transferred upon publication to the repo. Okay, and then it looks like this. Just an example for the synthesis from an amine, we come to a guanidine, and then you can see, aha, this is a reaction. This is directly coming from the Chemotion repository. And if you're interested in this, then you can follow really into the details of this reaction. For example, check, aha, they have published an NMR data, and if you're interested, you can really download the raw data and can look if there is dust in our spectra, for example, or if there are problems. And normally you also try to get all the data together to have NMR data, IR data, and mass spec data for such organic compounds. Should be, yeah, then you get also the assignment for this. I mean, this is now not perhaps the most beautiful way to show this, but if you want to make this complex again, reproduce our complexes, or this, in this case, a ligand, you can just download the data, make an overlay with your data, and check if your data is really fitting and if this is all reproducible research, for example. So just for this article, for example, we deposited 28 compounds in the Chemotion repo, which is now freely available, and you can find it if you download our article in Chemical Science, which is a Diamond open access journal. So there are all the links to the Chemotion repository, but you can also go to the Chemotion repository and search which guanidines have been published here. Or if you don't know that it was published in the Chemotion repo, you can also look into the PubChem database, because at night all these databases talk to each other in a simplified way. And then you can find directly our structures, our spectra, our information from PubChem to the ChemMotion repo, and from there it's also linked to the article back if you want really to read about the science. But the problem is that the ChemMotion ELN and the repo is for the molecular data, for the synthetic data. We did also a lot of DFT calculations, and there it's easy to put them all as a bundle into Radar for Chem, which is also a repository where you can put your annotated data. And again, here we have a DOI. So every molecule has a DOI in the ChemMotion repo, and now our full data set for this publication has a DOI to get all the DFT coordinates. So if someone wants to take the DFT coordinates or the computed coordinates from the complexes and wants to go on for further calculation, he or she can freely download them from Radar for Chem as an example. So this is some kind of best practice. And now I would like to go on to the teaching. It's always difficult to integrate into curricular teaching because changing teaching processes in the German system is not so easy. But for example, I'm lucky, I'm teaching in a master's lecture, and there I'm teaching sustainable coordination polymerization catalysis, and these are up to 100 students normally. And because this is the master, I can freely change this lecture. So I cannot change the title, for example, because it's in the curriculum, but I can change a little bit the content, which means that I can, for example, use case studies to explain the chemistry, the polymerization catalysis, and herefore I use then case studies with good and bad research data management, and also support this with integrated videos on RDM, so that the people really learn what is fair chemistry, what are the basics, for example, of a data management plan, and give some examples of good and bad RDM. And this is quite smoothness because it's going quite seamless because it's still the lecture, but it's not a pure research data management lecture, but it's a normal classical chemistry lecture, but with interactive units, and also now with this RDM examples as some kind of meta skill. And the students quite like it. Going a little bit further, how can we implement the practical use of the ChemMotion lab notebook in teaching? Herefore, we wrote an article which has just been published in Chemistry Methods because we thought it would be good to explain how large groups, at the moment we have around 30 co-workers in my group, how we can integrate the lab notebook ChemMotion into our work. And I just made some examples. For example, we are working here as well with guanidine complexes, but we use guanidine carboxyl complexes as NO donors with zinc, or we decorate them, for example, here with other substituents, or we use iron complex to perform the ring opening polymerization to obtain bioplastics in the end. And I have so many people now working in bioplastics, and some are working on the zinc side, some on the iron side, some use the iron complexes to use it for recycling in the end. So it's important that the students talk to each other, but we are spread over 3 buildings. And so I have sometimes the impression that the students do not talk enough to each other, but by using the working group repository, so it's the internal repository, they see who is doing what and who can question if a synthetic step is not working, or if anyone knows if some iron complex has already been done by some internship student or by master student. So this is quite practical because you can really then search for the substances. This is now screenshots from the ChemMotion ELN. You can really look for the details. How often has this been cooked or synthesized? How do the NMRs look? And all this unpublished stuff as well as a working group repository. And what's also really good, we have developed guidelines, internal guidelines for sharing the data. So for example, if I have a master student and he or she is collaborating with a PhD student, then it's important that they can collaborate, but that not the master student who is just learning to use the ChemMotion is deleting data, or that an internship student is deleting data. And so here's really a system how you can check who is sharing data with whom, who has the allowance. It's also important for the knowledge transfer between the generations of students. And also if you have a master student who wants to change the topic, change the group, for example, where is the knowledge in the end? I mean, a PhD student is publishing his or her data normally in the end, but the master theses are a little bit gray, I would say, in literature. And it's important to also capture that knowledge. And there are different permission levels. And the funny thing is, we started this 2.5 years ago. In the first, the students were a little bit, I would say, mourning. Oh, it makes some work. It takes so much time. But in the end, now after 2 years, everyone is using it. And already our internship students learn it, how to use it, and they can share the data again with the PhD students. And so it pays off that the PhD students are teaching it to the internships and to the bachelor students, because they can really easily collaborate with this, compare the spectra, look for errors, synthetic problems, and discuss this. So the organization of work is getting better by this. And this is now described in that paper. If you have questions on the Chemotion ELN, there's also a set of introductory videos in English. And also there we have a comprehensive online manual, which is called our Docusaurus. And we also have a practical help on the student level now. At the moment, it's in German. So we have a German set of videos, which is just translated in English for further usage, for lab stages, or for bachelor students, for master students. We saw that a PhD student is really tough normally to get through all these explanatory videos, but for the bachelor students, it's sometimes too complicated. So you have to make smaller YouTube units, I would say. Going a little bit further, we then integrated Chemotion into an advanced lab stage in the 5th semester in Aachen, so for 100 to 130 students. And again here, they get videos on the basic research data management, the FAIR principles, what are metadata, what is INCI and SMILES, and then they use it really on the practical application of synthesizing ferrocene, which is a multi-step process, on completed processes in the Chemotion, which means that, for example, they have to crack the dicyclopentadienyl dimer to the cyclopentadiene. Then they, for example, let it react with sodium. They produce their own iron 2 chloride, and in the end, they combine the iron chloride with the sodium cyclopentadienate to the ferrocene. Don't wonder that the ferrocene is looking a little bit ill here. That's due to the old version of the INCI. I hope that next year there will be a better version of the INCI. I come to this at the end. And so by this, they have the possibility to really describe their synthesis, how much stuff they weigh in, and how long it is boiling, for example. In the end, they can integrate the NMR spectra. Okay, an NMR of ferrocene is quite simple, but just by the principle to show this. And then they have their protocol also in the Chemotion ELN. And the students really like it because it's digital and quite seamless in this way. Going a little bit further, we then performed a SOCI survey of the last 2 years. It's running in winter term, with about around 40 students answering, and we are quite happy. I just want to show some of the results of this survey. If you look at the orange bars, it was 2 years ago, and the blue bars are 1 year ago. And I have the impression from the orange bars that in the first year they said it's medium to difficult, and in the blue year, now last year, in the second run now, they say it's easy to use. So the majority of students is more on the right hand side and say that it's difficult to use, which is a good sign. So from year to year. And do you think that you could use such a system for documentation? Was the next question. And they say that, yeah, the blue ones say yes, that they can use it after days or weeks, for example. So also here is a good trend. And if you go on that, if the chemical documentation will be in the end faster or slower. In the first year, the orange people said it will be slower, but interesting, last year now the second one said it will be faster in the end. And this is quite interesting to see how students think about this. And of course, now the practical lab stage is again running, and we will perform in February, March, the next type of survey on this. What we will also do is the work on molecular representations. As I told you, inorganic chemistry has a small problem because bonds are broken. I have to move. There's this bloody window here in the middle of my slides, this GoToWebinar window. So for example, if you look at cisplatin and transplatin, the problem is that if you compute the SMILES code for this or the INCI code, it's for both forms the same, which is a problem. So for example, if you look in PubChem or in ChemSpider or in the SciFinder for transplatin, you will get all the data for cisplatin. And cisplatin is a really wonderful drug for already, for more than 50 years, whereas transplatin doesn't have any importance as drug and no activity in the biochemical regime, which means the SMILES has a problem and the INCI has also a problem. And the problem is really deep lying already from the construction of these two types of molecular representations, because by definition, really from the start of SMILES and INCI, all the metal to anything bonds are broken. This is called the disconnection approach. It has a simple reason. If you look into an organic molecule, for example, like aspirin, you have defined covalent bonds. Wonderful. A C-C single bonds, C-C double bonds, C-O double bonds. Wonderful. Organic chemistry is a wonderful example where you have normal traditional bonds. You have normal, wonderful Lewis structures. And so this is for chemoinformatics a wonderful case. And so chemoinformatics really, I would say, focused over the last 30 years on organic chemistry, and also machine learning is running wonderful in organic chemistry. And inorganic chemistry has always these bloody metals, I can say it like this, and this poses problems for every kind of molecular representation. Also, if you look, for example, in ferrocene, it depends how you draw ferrocene, and you can imagine 5 different inches for one ferrocene. So you have both types of error in databases. You have for different molecules the same inchi or the same smiles, like cis and transplatin, or you can derive several smiles codes and several inchi codes for one and the same molecule, which is also bad if you want to reuse the data and make something useful with all this data. So 2 years ago, we started to involve intensively in the INCHI subcommittee on molecular inorganics. And meanwhile, we could work towards a mind change on the formal bond breaking. So this means in the next upcoming version of the INCHI, I hope it will come up next year. So I'm just hiring one and a half developer to work on this in Aachen, together with the full INCHI team. That we are working towards the non-disconnection approach, because by this INCHI will be feasible for inorganics and also for machine learning in the next case. This is also complemented by a total different approach, because with using smiles in INCHI, you always have this Lewis picture behind. But if you think of inorganic compounds, of cluster compounds, the formalism of a single bond, a double bond, is led to absurdum. You often have shared electrons, multi-centered bonds. You have electron deficient systems, systems with too many electrons, cluster compounds, where it's not clear if it's a 2.5 type bond or anything. And this makes it really complicated. And so in this case, to use all the data and the topology of metal complexes or organometallics also, it's better to work with graphs. And here, together with the Schatzschneider group, we have developed an alternative to INCHI, which is called TUCAN. The CAN comes from canonicalization, where we really take such a molecule with all the protons around and canonicalize it for the sake of its topology, and then come from this, for example, to graph neural networks. TUCAN in itself has just been published, and we see it as some kind of forerunner to also inspire the INCHI work to lead the INCHI into the modern world, I would say. Okay, these are the updates from NFDI for CHEM, and I hope I could convince you that by this work we make knowledge accessible. So in the end, it will be fair data and also sustainable. In the best case, open, of course. So the CheMotion repository is open, the radar for CHEM repository is open. So by this, fair data and open data are shaking hands. This will, on the long range, accelerate research, make it also more reproducible, and lead to really cool machine learning applications in the end. I think Theo will come to this a little bit in some minutes. And yeah, by this, I would like to thank you for your attention, and I'm really happy to answer every kind of questions. And thank you. Okay.
Thank you so much, Sonja. It was great to hear all this about what you're doing in chemistry and in organic chemistry in particular. I was waiting for answers. Please feel free to just type your question, in the question window. While we wait for a couple of questions, I was wondering especially about the electronic notebook. So you mainly dwelled on the CheMotion notebook. Are there any other open electronic notebooks that you would advise, and what would be the pros and cons of alternatives?
Yeah, what I can also advise is eLab FTW. This is really good for physical chemistry and biochemistry. Nicolas Carpi is a developer, and we are also collaborating with him. If you have, for example, you have a microgel or some polymeric sample, then you have a different view. You take your sample, the sample has some name, 1, 2, 3, HK or something, and then you make a lot of measurements with the sample. And for those people working like this, a lot of in physical chemistry, for example, ELAB FTW is quite practical because here you can store all the data for your sample together in this electronic lab notebook. But if you want really to report chemical synthesis, that is not so easy in ELAB FTW, because there you can put in the chemicals, but as pictures. Or using the Inchi code, for example. And this is easier in Chemotion, because if you're really doing synthesis, then it's easy to draw your molecules or to put in the ChemDraw, for example, or if you're using Marvin is now open source as well, and then it's easier. So if you have a molecular-centric way of working, Chemotion is really good choice. If you have a sample-oriented way of working, or you are more on the methodology side, or for example, you are developing basis sets and computing a lot of stuff, then ELAB FTW, I think, is the better way. Or if you're working a lot with proteins, there are also biochemistry modules in ELAB FTW.
Okay, great. And if I mean, Theo, also, if you would like to join the debate here, you can just jump in. But because I'm curious on the next step. So there's already a couple of databases for chemical reactions. What is your view on that? I mean, if you'd like to just start exploring some reaction data, where would you start from, and what are the current falls on these databases?
For example, if I want to know who has done anything, I would look into the SciFinder, for example. Yeah, I mean, that's a commercial database, and I think it's one of the largest. So for me, it would be practical to look into the SciFinder and then follow the publication. And then I find the publication where it is written, aha, we did it like in reference 33. Then I would look into the reference 33 and go on all this chain in a traditional way, because the actual FAIR databases are not yet large enough.
Yeah, so that's it. Then we come to the conclusion for open notebooks, for electronic lab notebooks, open source stuff is there and is useful, but for the reaction databases, we are still not at that point, is it?
Not that point. I think, for example, there is from Connor Cowley, there's an open reaction database, which is also growing quite fast, the ORD. It has a more organic focus, I have the impression, until now. But I mean, it depends how much data you get in. All these databases are growing, and they have to grow. And if they are interconnected in the end, then it will be even better.
Okay, perfect. I see now we have a question on the chat. So you mentioned that some people are hesitant to take up the use of ELNs and data sharing practices. For you, what is the most convincing argument to break the initial barrier? That's the question.
The problem is that there are different reasons for being hesitative. From the PhD student side, it's just, it takes time. In the end, you have to learn it. It takes really time to learn to use Chemotion, or if you use GlabFolder or any other work, ELN, for example, first you have to invest some time. And they think they do it just for their boss normally, but in the end it pays also off for the students. I know so many colleagues, and I even had it in my own group. You always tell your students, if you have a new compound, you have to make the IR, the MS spectrum, or the Raman spectrum, the NMR, and all that stuff. And almost when they start to write up, of compound 33, I need still an NMR, or I need a good depth spectrum, blah blah blah, and then they go back into lab to make some substance. Although you always told them over the 3 years that they have to keep their data together and blah blah. So with using an ELN, they have more order in their data. It costs some time, but in the end, writing publications, writing the thesis will be easier. And I have also the impression, just from the last 2 years, that the students, or just the absolvents having the PhD, have a good competence in this. So the industry loves to take people. I hear from my students, but also from the colleagues, that if a student is not only writing, I'm good in doing synthesis and good in doing NMR spectroscopy and all this wonderful methods, but I also have some experience with data management plans, how to put the data in a fair way, in a manageable way, that this is a competence which is an add-on to all the other competences, and so that people get easily a job. That's also a new competence to have in mind, not only for academia, but also for industry positions. So I think the time invest is a good invest, but I also have the impression that the ELNs have to get more user-friendly. Sometimes it's just a missing button here, and we are really closely collaborating with the ELN team. So I have one developer in my group, and he's the channel to the main development team in Karlsruhe, guided by Nicole Jung, which means if we say, for example, it would be good to have some catalyst module to describe catalytic reaction better in the Chemotion ELN, then they can make a module, and in the next version of Chemotion, it will be then available to the whole public. So Chemotion is not made in stone, but it's dynamic. And if you have interest and say, I need a biochemistry module, or for example, there will be a polymer module, I think in the next month, then it evolves. It's just evolving during NFTI for Chem, but also within other projects. And this is quite practical. From the other side of the professors, I have the impression that a lot of colleagues are fearing that the productivity of their students is going down a little bit because they have to invest more time into the documentation of their data, and that competitionists may have a too large advantage if all the synthetic details, the secrets, are published openly. So some colleagues share their data quite willingly, also if they are not published in an open way. If you give them an email, oh, I would like to cook this and this, and I have a question, what was the silica gel and all these details, and they willingly mail you all the details, wonderful. But there are also colleagues that make some kind of cascade hidance, I would call it, that they say, yeah, we have been inspired by synthesis by colleague X and Y in reference 33, and then you look in reference 33, and there's the compound which has been synthesized following a procedure like in reference 38, and by this the knowledge is really well hidden and it's difficult to reproduce the stuff, and sometimes the colleagues really want to hide it.
But I think that's a very good argument to convince people to share data. I mean, we all want to read papers in which all this is clearly disclosed such that we can reproduce the synthesis. So if you do that, your paper will be more read than papers next that won't disclose the synthesis. I mean, nobody likes to go to the lab and not be able to reproduce because the procedure are just not clear. So I think it's also a very good argument. And to add on this and then move to the next question, I guess you are aware also, Sonja, there's the State of Open Data questionnaire that Springer Nature does every year, and that also gives a picture a bit about the motivation. So if one is curious about that, you can check that the State of Open Data. It's something that is released year after year, and also gives a bit the trends on funders are pushing and which kind of motivators are needed to get scientists, to get us to publish more open science and open data.
I would call it the carrot and stick approach.
Yeah, exactly. We have a very nice question, and the question is, often open science is reduced to open access and the publishing charges. How to address this? I mean, how to go beyond just open access papers?
Yeah, open access is great. And if you have good tools for fair data, then open data is easier. So if you lower the technical hurdles to put your data in a fair way, for example, like in the repo as I showed as example, then that data is already open data. So that's quite easy.
Okay, great. So I don't see any other questions now. I don't know, and if you had seen any question passing, we can still go on that. Else we'll just move to Teodoro's presentation. Okay, so let's kick off with Teodoro. Teodoro, thank you so much, Sonja. It was great. Sonja, of course, will still be with us because we'll have a debate, a short debate just afterwards to see where we can go and which great things can we do to steer open science and the models that come out of it, which is exactly what Theo will be talking to us today. So Teodoro works as a distinguished researcher and manager for IBM Research Europe in Switzerland. He studied in Pisa, Italy, where he also received a PhD in computational chemistry in 2006 under the supervision of Michel Parinello. In 2008, Theo joined the IBM Research Zurich laboratory. His research interests focus on developing machine learning and artificial intelligence technologies to digitalize chemistry and material science. So exactly what we need and towards where Sonja pointed. In 2022, the team received the Sandmeyer Award of the Swiss Chemical Society for the important contributions to the field of digital chemistry. So we are all looking forward to hear from you, Theo, on the great research you have been doing.
So thank you so much, Pedro, and I'll be building on top of what Sonja was presenting to give somehow an overview of what we can do once we have data that is publicly available, and in general how this can really address some innovative changes in disciplines like organic chemistry. And this is going to be one example, but we could translate mostly one-to-one the things in other area. So first of all, thank you, Pedro, for the very nice introduction, and thanks also to the organizers for having me here today afternoon. Everything that I will be presenting is, of course, the outcome of a work of quite few people, some still working with me, others that have been leaving the team for building their own careers. And so stick always their face to all the topics that I will be presenting in the next minutes. So one of the things that I would like to address is, of course, when we talk about synthetic organic chemistry, we talk about data and chemical reaction. And of course, I mean, we always have in mind to make a molecule in the lab, and this scope, this objective, is normally translated with a series of synthetic steps, a procedure that brings the person closer to the synthesis. Of course, I mean, when we talk about molecules and behavior of molecules, reactivity, even myself as a computational chemist, I tend to think the quantum mechanical way of treating molecules, and that's of course a very compelling part of the entire ecosystem of possibilities. But in reality, in this talk, I'm not going to cover anything related to quantum chemistry, but instead what I will be doing is showing how you can use data that is available, possibly through ELNs or even through publication in journal articles, for improving our predictive capabilities on very complex procedure tasks, like the synthesis of a specific molecule. And when we talk about the synthesis, we have to keep in mind that we talk about two parts. One is the synthesis design, the other one is really the implementation. Synthesis design is nothing more than compiling a retrosynthesis, which is the designing of making a molecule by walking backwards, starting from the final target all the way to more simple building blocks that eventually are also commercially available building blocks. And the second part, as I mentioned, is actually the synthesis execution, which basically means if you have the design of the synthesis, if you have a retrosynthetic analysis, this does not necessarily will not necessarily translate into a success story in the lab. There are many variables, including physical parameters, but also the choice of solvents and a large number of variables that can affect the final outcome. And so the second part is really the details of the retrosynthetic analysis. So how are we going to translate every single reaction in the retrosynthetic analysis into a sequence of steps that are maximizing the success rate? So the very first thing that I will be telling you is, and maybe some of you already had the occasion to listen into that, but one of the things that really captured our attention, which is at the same time very fascinating from a person like me coming from a computational chemistry world, but also that is reinforcing the belief that is in many organic chemists, that there is a language underneath chemistry. And that language is actually more profound, more deeply rooted into the discipline than just what we may think when we talk about a language in a chemical context. So I'm referring here to the fact that we are not using a natural language like English to describe chemical processes, but we are really using a certain number of symbols, characters, that only when they are combined together in a meaningful way, so this means obeying specific grammar rules, they really make up a sentence, a chemical sentence with a specific meaning. And so if you think of a chemical reaction like the one depicted here, like a sequence of words, every single molecule may be a word, and you consider that there are specific rules when you can combine different words in order to have a chemically meaningful reaction, then suddenly you understand exactly what I mean when we talk about a language. In this language, the words are the molecules, and the rules are, the grammar is nothing more than chemical reaction rules describing the reactivity of the molecules. So we don't use a graphical representation for this molecule, we use a linear representation, a linguistic representation, which is a linear sequence of alphanumerical character. This notation is called smiles, and basically every single molecule is represented with a certain number of alphanumerical terms. And basically, when we look at sentences, now let's think of what Sonja was presenting us about electronic lab notebooks. When we think at sentences like records extracted from electronic lab notebooks, then suddenly you can see that every single chemical reaction can actually be seen as two parts. One part is the part of the precursors here, and the other part is the part of the product. So these are like two completely separated sentences, one expressing in a language which is the language of the precursors, and the other one expressing concept in a language that is the language of the products. And so when we initially started exploring the possibility to apply language models to chemistry, we thought of a chemical reaction like a translation tasks between two different languages. So very similar to training architecture that are translating between English and German, here we can train architectures that are translating between the language of the precursors and the language of the products. So that's very simply said what we mean when we say that there is a language in chemistry. If this wouldn't be the case, it would be very difficult to train architectures that have been intrinsically constructed and developed for absorbing the knowledge of a specific language. And so forward reactions or chemical reactions are actually nothing more than a translation between two different languages. And we can train models that can learn the chemistry by exposing the architecture during the training stages to a large number of chemical reactions. Every single chemical reaction will be describing a specific reactivity. We will be absorbing the reactivity of the sentence by training on a large number of these chemical records. For doing that, we use an architecture, and I promise I will not go more than that into the details, that is called a transformer. It's very, very powerful because actually we are not codifying any chemical reaction rules. We are not integrating chemical knowledge into the software. Everything that is about chemistry, we are just learning directly from the data. And this offers, of course, I mean, a quite high degree of variability. Imagine, again, reconnecting to what Sonja was mentioning, you can on a certain base, weekly base, monthly base, you can ideally extract all the information that you have captured in your electronic lab notebooks, and you can reprocess the same architecture for improving the type of chemistry, so for adding chemical knowledge to this architecture. And it's also very interesting that between all the different machine learning data-driven approaches for treating organic chemistry, this approach based on languages is still today the most accurate way of extracting chemical knowledge and predicting the outcome of chemical reactions. Now, why did I spend so much time on telling you about the language? Well, because if it's clear that a chemical reaction is can be seen as a translation task between the language of the precursors and the language of the product, when we want to predict a product between multiple molecules, what we do, we just act exactly as we would do when translating a sentence from English into another language by using online translation services. And so here we would actually ask what is the output of combining a certain number of molecules. But at the same time, you can ask the opposite question. Given a molecule, given a sentence in a language like, for instance, Italian, what is the corresponding sentence in English? I mean, for the sake of translation, this task is dual. It's basically equivalent. But from the context of chemistry, this process is completely different. It's not anymore the prediction of a chemical reaction, but is actually the design of a retrosynthetic scheme. And so you can, how do we address that? I somehow spoiled the entire problem. We can simply swap the order of the data and retrain exactly the same architecture. By doing so, we will be learning how every single target molecule can be decomposed into more simple building blocks. And again, it's always a translation task, and it's the dual, the opposite of predicting the outcome of a chemical reaction. Now that we know how we can assemble a retrosynthetic design, so we can collect data ideally from ELN, but eventually also from publication, journal articles, and we can compile a large corpus of chemical reaction that we can use for training forward prediction model, but also retrosynthetic model. The next step is actually the one of focusing our attention on the details of every single chemical reaction part of the retrosynthetic analysis. And so how do we address this problem? Or even better, how is this problem addressed routinely today? Well, the problem today is normally addressed by looking into databases. You may be looking, for instance, into a database of extracted chemical reactions from electronic lab notebooks or from journal articles, and try to identify schemes that are very similar. We decided to follow an approach that instead is building entirely on learning the correlations between chemical structures of the precursors and the individual actions. So one of the very first challenges that we were facing is that while there are public databases of chemical reaction, there are no public databases of experimental procedure. And so the very first thing that we had to do was building the corresponding, it's an equivalent of a book of cooking recipes for chemical synthesis. And so how did we do that? We had to extract text, and we have been working almost essentially with patents, but we had to extract the text from patents that were describing the detail of an experimental procedure. And the sentence that you see here on the left is an example. So the other thing is that we built a model that was taking every single of these paragraph sentences and was translating these paragraph sentences into a coin size sequence of operations. And the reason why we were doing that is that the paragraph on the left is very hard to interpret by a computer. Instead, the coin-size sequence of operation is way easier to be processable by machines. And so for every single experimental protocol, whether ideally it's reported in an electronic lab notebook or described in a patent or in an article, we were actually in the position by using a natural language processing model to convert that text, human readable, into a text that instead is machine processable. This was the very first step. But then the second step was that each of these paragraphs was describing a specific chemical reaction. And so what we were doing is you have a coin-size sequence of operations here on the right-hand side, and you have the corresponding chemical reaction that is described by that sequence of actions on the left. And so the next thing to do was actually to construct a machine learning model, a data-driven model that is taking as an input the entire chemical transformation. So this means precursors, products, and everything. So solvents, catalysts, anything that is useful for describing this transformation. And you are feeding this information as an input to a machine learning model that is actually predicting as an output the corresponding sequence of steps that are required in order to run the chemical reactions in the lab. And so in order to do that, we were taking every single paragraph as described before, converting into a sequence of steps that are machine processable. And then we were also abstracting this information. So this is only to be sure that the model was able to capture the correlation between the presence of specific functional group, the structure of the molecule, with the corresponding action in the experimental procedure. So what we are trying to capture here is something that is very powerful in terms of the knowledge that is intrinsic in the data. So we are trying to capture, for instance, when a chemical reaction is exothermic and requires to be cooled down. This is a specific operation that is coming from the data. Or when the solubility of a specific compound that maybe is an intermediate is actually decreasing, and so you need to have in place filtration steps and so on. This is really the essence of this operation. We were trying to capture the correlation between every single action and the structure of the molecules characterizing the chemical records. And so all this, of course, with a data-driven model. And in essence, this is really one of the pictures that, in my opinion, describes best the entire work that we demonstrated that is possible to do. So you don't exactly the feeling that people have in the lab. Many times you talk with synthetic organic chemists, and they, by looking at the molecules, they can tell you whether a specific molecule is soluble in a solvent, or the reaction maybe is going to be exothermic, or you will have the formation of a precipitate. I mean, what we classified like experience in reality is nothing more than a correlation that experts have been acquiring through many years of experience between the structure of the molecule, the presence of specific functional groups, and the corresponding actions. And again, we try to capture exactly the same thing by using exclusively data. And so, of course, I mean, one of the last things that I wanted to show here is how can you use all this data? Where are the frontiers in the future? Well, the frontiers that we try to imagine in our team are the ones of now that you have in place a way to digitalize synthetic organic chemistry. Well, the gap between operation, manual operation in the lab and autonomous operation in the lab is incredibly small. What I described before is actually was the missing piece for implementing an autonomous lab, where ideally you can design, you can draw your molecule, your target molecule through a web browser, use the machine learning model for designing the retrosynthesis, but also for designing the sequence of operations that have to be implemented in the lab, and then send the entire set of instruction to commercial automation hardware. So this is really a very, I would say, a very visionary view, and somehow this is exactly what we implemented. In terms of, for curiosity for people that may be interested into the details, how that works. I mean, in terms of commercial automation hardware, we decided to opt for one vendor among the few that are producing hardware for automation in the lab. And for this specific implementation, we rely entirely on batch synthesis. We are talking about reactors that are around 100 milliliter in terms of volume, capability of handling liquid, solids, and performing a quite wide range of operations compared to what the human operator can perform in a chemical hood. And we attached also analytics in this specific case, again, for this prototype, an LCMS and a benchtop NMR, both of them for monitoring the fate of a chemical reaction inside the reactor. So basically, we use the analytics to either prove or check the quality of the prediction of the machine learning model in terms of retrosynthesis and in terms of action prediction. And this short movie is actually what you can really experiment from home. We positioned, of course, a series of webcams. This is more for fun and engagement than else. But it really gives you the perspective of where you can go with digitalizing chemical tasks thanks to the use of data. All this would have not been possible by simply codifying common knowledge. You had really to rely on the intrinsic bits of information that are in chemical data reported in literature, in ELN, in patents, for building models that can then drive a robotic system for performing lab operation. So what else can you do with data? Well, that's really the beauty, because once you start scratching and you understand the enormous value which is stored inside data, then you can really be very creative. And this is somehow a very short overview of what we have been doing by always using chemical data. So one of the very first thing is you can use data to curate data itself. So, and this is normally a very cumbersome task, very tedious task. Every time we talk about data, we talk about ELN, extracting records from ELN. We always keep hearing it's going to be a very, it's going to be a nightmare, a very tedious task, because there are going to be quality issues to be resolved. And somehow you can use all the data-driven approaches, or some of the data-driven approaches, for actually curating the same data. The approach that we follow, and I'll try to explain it with layman terms, I mean, without going too much into the details, is very simple. If you try to learn a language, let's imagine that you are trying to learn English as a first foreign language. So, and you try to learn English by learning with examples of sentences. So let's imagine that I give you a certain number of sentences that are consistent with the English grammar. And from time to time, I show you example of sentences that are actually in a broken grammar. So it's broken English with an incorrect grammar. So by doing so, you will start understanding that those sentences do not match with the other sentences that you have been exposed previously. And so you try to adapt whether the rule can be generalized in order to cover other cases. But at a certain point, you will be really seeing those sentences as outliers in learning your foreign language. And so we do for dataset curation. What we do is we look at the frequency that some architecture are showing when they learn a large number of records. So there are frequencies of learning and forgetting specific data records. And by looking at the fingerprints of forgetting and learning, we can identify outliers of distribution. But you can also use the data for actually building reaction classification. And this is very important, for instance, for exploring the chemical reaction space. Maybe even one day arriving to the design of not yet existing chemical reactions. But in order to arrive there, we need to be in the position to explore, to define the space of chemical reaction. And so we used the data for defining what we call reaction fingerprints that, again, can be used for building very nice atlas, but can also be used for a larger number of tasks. You can use data for predicting reaction yields, and this is actually a very important task, especially when you are in the lab and you have been spending maybe 10, 15 experiments trying to improve the yield of a specific molecule. Well, you can use the data for actually guiding you towards a more successful design of a synthesis with higher yields. And you can also use the data for actually learning how the atoms are mapping between precursors and products. Now, this, in my opinion, is one of the most fascinating things that the data contains, that the data, chemical reaction data can actually give us. And I mean, I don't know how many of you really have a clear idea of the effort that takes in order to map one atom from the reactants, from the precursors all the way into the products. So it takes radio labeling a specific atom, so having a molecule with a radio labeled atom in a specific position, and then really performing all the analysis in order to understand where this is going. Surprisingly enough, I mean, we show that actually the data, the information of where the atoms are moving from between precursors and products can actually be extracted directly from a very large, consistent data set of chemical reaction. This means without labeling the atoms, without labeling the data, you can actually build models that can tell you with a very high degree of confidence where the atoms are moving between reactants and reagents. So you can also do things that are very, very interesting. You can use the data, for instance, for trying to promote different types of reaction synthesis protocols. And this is the example, for instance, for enzymatic catalysis as a part of the effort within Swiss coordination project, which is called NCCR catalysis. We are really building and promoting the use of enzymatic catalysis instead of traditional chemical catalysis. And that's as simple as treating an entire enzyme either with a tokenized way. So it doesn't really mean, I mean, one way, of course, is treating the enzymes with a linear sequence of amino acid, but the other way is just to have a very simple classification scheme that is identifying the enzyme. And so by doing so, you can really build that relationship between the catalyst and the effect that the enzyme may have on specific chemical transformation. I'll stop it here. And I hope, I mean, I managed to give you a very quick idea and overlook on how you can use the data once the data is in a form that is easily digitally processable by machine. So again, thank you so much for your attention, and looking forward to any question you may have.
Thank you so much, Theo. It was so nice to see all the examples we have of applying machine learning to open data. So while we wait for some questions, let me just start by asking on converting these human readable synthetic routes to machine readable routes. I mean, as you said, you applied NLP to do this conversion. It all sounds very smooth, but of course there were some hurdles on the way. Can you tell us, and especially to people that want to apply NLP, what were the main challenges you faced and how you solved them?
Yeah, no, that's it's true. I mean, I apologize for having given the impression that was a very simple task. In reality, the task in itself was incredibly painful, and I can say that all this went through a series of steps that were really trying to mitigate the major issues that you have in heterogeneity of data. So what does that really mean? You may have different people reporting different recipes. You may have different backgrounds, and this of course is reflected in the way people are writing and reporting the information. Now, if you want to build one model that can deal with thousands or tens of thousands or hundreds of thousands of people reporting information, that model needs to be properly constructed. And so definitely the greatest difficulties that we had was that there is a certain distribution, like for instance, when authors are publishing in journals, even if we take a monographic journal on a specific theme, different authors will have different styles of expressing the same information. And so it was very difficult to be able to train an architecture that was able to capture all these heterogeneous background between people on how the data is presented. And yeah, this required, of course, I mean, weeks of annotation. It even required to have only one single person acting as quality controller for all the annotations in order to have a very consistent set of examples that then you can use for training your architecture. So very simply said, but in reality, a work that took months. So you spotted, Pedro.
No, it was a great work. I was just curious about the main challenges, and just to wrap on this, how many papers at the end you needed to train your network?
Yeah, no, this is another very important one, and it's something that I want to reconnect with the plea that also Sonja was making about the use of electronic lab notebooks and the cultural change that we need to have in place. So on average, we train the model for predicting the experimental procedure on almost 700,000 experimental procedure. This may look like a huge number, but in reality, for the task that we were trying to achieve, is an incredibly small number. And it's very simple to understand why 700,000 is a small number. It's a small number because we are trying to capture the correlation between having specific functional groups or specific functional structures with the downstream effects. So when we talk about, for instance, we were not training a model that was trying to capture or trying to mimic the thermodynamic of a reaction. We were not trying to build a model that was able to predict the solubility. In reality, the model that we trained was trying to do all these tasks exactly at the same time, because every single action is connected to either the thermodynamic, if you have to cool down, for instance, or you have to heat up, is trained to the physical and chemical behavior, like solubility. If you have the formation of a precipitate, then you actually are in the need of performing a specific action, like a filtration action. And so, considering that the molecules are a large number, I think some of the estimates say 10 to the 60 or so, and we are only using 700,000 procedures, probably covering only, I don't know, few tens of thousands of different molecules. You can really see how challenging that was. So we would have loved really to have more, and I personally still believe that there are many opportunities that are untapped, that are unexplored, between what publishers like Willy, for instance, could enable, thanks also to the data that I mean authors publish on journals.
On that, and maybe Sonja can also join us here, and then I'll go to the questions. But this is a very interesting point. I mean, what was the oldest paper you used, and is there a barrier on that? Because also Sonja mentioned about old files, but we are also, so old files are behind the paywalls of paid software, but there are also all these old papers and not, I mean, chemical knowledge that has been there for at least 100 years that we need to untap and we could use. So what was the oldest paper, Theo and Sonja? What is your view on getting the data from these old papers?
So I can answer regarding the first part. I mean, we didn't use papers, as I said. I mean, we used patents, but we went all the way back to patents probably way older than 50, 60 years ago. So I think, I mean, that there are examples that are very, very important, very interesting. And then I let the stage to Sonja to comment also about that. But one of the things that I wanted to say on the second part of the question is it depends a lot on what are the objectives of the people using the models trained on data. For instance, it's really questionable whether you want to have, if you are working, for instance, in an industrial environment and you are dealing with production optimization, do you really care whether your model can capture, I don't know, the chemistry behind the use of a Grignard? Most likely, they will never be using a Grignard in a production environment. So quite often, it's easier to build a model that can that can leverage more recent knowledge that is way more interesting for specific application. But if we talk about educational context, then it's a completely different story. You need to build that trust in the technology, and for doing that, it's important that you try to capture as much chemistry as possible. So I don't think that there is an answer whether you can really, you have necessarily to have all the chemistry going back to 150 years ago, or necessarily focus on the most recent one. Depending on the context, one or the other option may be very valuable.
Okay, very good. So that was about my question. And if we want to build a model that can capture all the chemistry since 150 years ago, how can we dig this from the old papers? What is your view on that?
So thank you first of all, Theo, for your cool talk. It was really amazing what's possible now. But this is all inorganic. It's all organic chemistry. Concerning now the question, what we do with chemistry. So in INFDI for Chem, we are focusing really the upcoming chemistry. So we enable researchers of today's world to put their data in a fair way in. And I think there are so many researchers working on, for example, language models to understand the old papers and translate old papers into recipes which are machine readable. So the machine readability of old papers, of the old structures, the old molecules, and the old descriptions, that is an own research field in itself. And I'm not in that research field, but it's a large task to take all this old knowledge. But I think there was a study which was published 2 years ago that every 2 years, the knowledge, the chemical knowledge is doubling. So we have to start now to capture our knowledge. Otherwise, in 2 years from now, we have the double amount of work to get all the old stuff from the archives digitized.
And that was part of my point. No matter how fast we start, we are already late, right? So
we are already late, but we have to start now, yeah.
Exactly. Very good. Okay, so I'll move to the question, and we can keep up with the debate. There was a question on ELN approaches, the added value of ELN approaches to machine learning, but I think Theo just answered on that a couple of minutes ago, how important it is to have the ELN for good machine learning models. There's also another question also for you, Theo. Obviously, machine learning models depend on the hyperparameters, so you didn't much talked about it, and there was one of our attendees that just asked the very broad question everyone would like an answer to, is how to choose the right hyperparameters. Do you want to give us a hint on that?
Absolutely. So this is a little bit the secret ingredient in the sauce. So there is not a specific protocol, but definitely the only thing I can say is that I can tell a little bit what is the approach that we follow in the team. We spend from time to time, depending also on the domain and the complexity, some effort in optimizing hyperparameters of the architectures. However, this is not a task that you do on a daily or routinely basis. So there may be specific tasks like reaction prediction, where you are interested in really optimizing the architectural infrastructure, read the hyperparameter, in order to have that model that is performing the best. And so we do that for specific operation, but quite often, once we do that, we maintain the hyperparameter, even if we keep changing underneath data set. So there is no free lunch. Every time you have to start a new project, of course, you will have to dig into the big question: how large is going to be my architecture? How am I going to address few specific parameters that are at the end affecting the performance of the prediction based on the data that I have? These are necessary steps, part of due diligence. Again, you don't do that daily. Normally, you do once on calibrated data sets, and then you can safely reuse some of those hyperparameters for future operations.
Okay, very good. What I would add on that is, open science best practice would ask us to publish the hyperparameters along with our paper. So I think that's the only way we can reproduce also machine learning models, and preferably to also explain the procedure that led you to this hyperparameter. So if we all do that, I think we'll all know much better how to get there, even though it's still quite empirical, as Theo was saying. There's another question. I apologize, I cannot always see who is asking them, but there's first a comment which is mainly for you, Sonja. The comment is, we are all discussing these very nice notebook digitalizations, but do we need that all community accepts this to start, or how to get the community to just join and make sure that we are all applying the same procedures and standards in what concerns electronic notebooks?
Perhaps I do not understand the question fully correctly. So it doesn't have to be for everyone the same type of notebook. I mean, there are so many electronic notebooks out there, the free ones and the not free ones, but they all have a similar structure. And so if you put your data in an ordered way in, all this metadata is directly annotated. So for example, if I make an esterification and put it into Chemotion, then I also can tag it with being an esterification. So I think all the data I put into the Chemotion repo could be easily reused by Teodoro in the end, because all this is already implemented in the Chemotion. So it's some kind of structured view to put the data in. But if I use, for example, lab folder or Cyformation to name two commercial ones, there's a similar type of putting the data in. Not just drawing the structure and let it run, but have all the ingredients in a controlled way and which concentration and which input from which company and which type of reaction this is. So you have ordered input. So I think it's not dependent which lab notebook you take in the end, but to put all the data in a structured way, to assemble the NMR data in a structured way, and wrap it together and then publish it together. That is an important part. But on the long range, it would be important not only to publish always the best reaction with the best yields. I think for machine learning models, it would be also interesting to have a medium good catalyst or reaction which is not running really well to 99%, but to also have negative results in the end in the databases to train the new models. I'm a totally different discussion here, but at the moment we are used to publish always the fastest catalyst, the best reaction yields. And I think I'm discussing this with some machine learning experts already. They told me, do you have data of slow catalysts? Yes, I told them, not published, but having it in my group, because no one can at the moment publish a slow catalyst.
Yeah.
And that really ties nicely to a question. Sorry, just to take the question from the audience, because the question was indeed that one. Have you come across negative results when doing the machine learning, Theo? And how important are these results for chemical space designing the catalyst, as Sonja was saying? What is the importance of the failed so to say failed results?
No, exactly. I wanted to connect with Sonja in view also of this question. No, I wish we would have encountered negative results, but we are in a very awkward scheme where you can't publish negative results, or at least, I mean, that's perceived in a very negative way. And I think this will have to change in the future, because I second and I resonate with what Sonja is saying. All these technologies that are intrinsically based on data at the moment are strongly biased, by the fact that we are relying on information that is published, and because people are publishing only success story or what should be success story. That's another very interesting parenthesis. Then you are actually missing the link with all the other important features that are telling you when the chemistry does not work. So in short, no, unfortunately, we didn't encounter negative data. However, I must say that we have been fascinated by the negative data. And so there is a person, one of the persons that you saw in the second slide, that is actually actively working now since more than 1 year. We do have an idea of how to embed the negative data into training schemes, and most likely we will be presenting some results in the next months. But still, this is only a technological advancement. What will have to happen is a cultural change. And maybe this is a plea also for the Willy team. I'm still looking forward to see, before I will retire, and I plan to retire relatively soon, hopefully, but before I retire, I would love to see a journal not completely dedicated to unsuccessful, and we have to define even the unsuccessful, but basically any type of results, irrespective of whether you can claim a 100% yield conversion or a 0% yield conversion, because that data, it's as important as the positive one, especially when there is a very strong chemical meaning attached to the experiment that you were trying to do. We are not telling that any negative data is important per se. That's not the message that I'm trying to convey. But when people are expecting that a specific transformation should happen, they test it and it does not work, well, then this is the element that can help a lot to improve the understanding of the chemistry and reactivity by data-driven models. There is always this estimate that negative to positive is more or less in a ratio of 10:1. So you can imagine how much volume of data we have been maybe closing in a drawer, putting somewhere and never used. So that's something that we should definitely reconsider. And ELNs, again, to reconnect with what Sonja was mentioning, are an amazing resource, because by tracking everything, you don't really, you are not biased to only present or only store something which is successful. So I think that would be, that for me, ELNs are really the due diligence for then a wider adoption of models.
I definitely agree on that, and I would say that, yeah, as of today, people just publish their reaction databases along with their papers. Of course, this will, I mean, you don't have to speak about or talk that much about this, the negative results if you want, Will, but if you publish the data along, the full data along with it, I think it's already a very good step, such that the data comes along, even if you still focus on the best results. But I definitely agree, we need everything to understand how things work. So for last question, as we are reaching the end, I'll go back to Sonja, because it's a very practical question. So I think Sonja is the last chance to convince people to really stick to ELNs, as we came to the importance of ELNs. So the question is really how much time you need to train a student to write his notebook in Chemotion, and what are the key steps to train a student on that?
We do this with our bachelor students. It's 2 days.
Okay, so that is rather
in 2 days they're fit. I mean, in the end, if they have complicated NMR analysis and they need some more teaching, but just drawing their reactions, what to weigh and how much stuff and where to get the chemicals and how to collect and to share the data with the others in the group, it's 2 days of training.
Okay, great. So I think that's indeed very convincing. Thank you, Theo. Thank you, Sonja, for a very nice talk. Thank you, Ali, for inviting me. I will just now hand it to Francesca for the closing remarks. It was a pleasure to be with you this afternoon. I think we had a very interesting discussion on what we can do with open data and how important it will be for the research in the future.
Thank you.
So yeah, we reached the end of this conversation. It was really interesting, this journey, and from my perspective at least, we tackled this issue from so many different angles. We saw from applying fair research practices to everyday life in a lab, to predicting reaction using like translation tools. It just shows how complex this journey is, this transition towards an open science world, and how many parties are involved, from the funding agents, the infrastructure, the education, and it also reaches out to many other components, like, for example, redefining what a success story is, like Theo was saying earlier. And of course, we as publishers need to be involved in this conversation, and we need to keep the communication channels open. And this has been a really interesting journey. And now, however, it's time to thank our speakers and our moderator for this interesting event. And for everyone else, yeah, we will share the recording of this event in the next few days. Thanks a lot, and a nice evening to everyone. Bye.
Thank you. Bye.
Bye-bye.
Bye.
Bye.